Welcome, students. Please make sure your English subtitles are turned on as we embark on this explainer. Think of today's session as your formal, step-by-step career guide into your foundational engineering studies. I am absolutely thrilled to be your guide through Unit 1, Building Science and Mechanics. As we kick things off, I want you to view this not just as another class, but as the literal foundation of your entire future profession.
Okay, so here is our roadmap for today. We're going to welcome you to the field. Explore the major engineering disciplines, master your basic construction materials, break down the anatomy of structural elements, and then we'll wrap up with some common professional errors and a quick quiz.
Let's dive right into Section 1, Welcome to Civil Engineering, laying the groundwork for society.
Before we even start looking at specific materials or complex formulas, you absolutely must understand our primary objective. Our job is transforming conceptual plans into practical, safe, and sustainable realities. As you step into this highly interconnected web of specialties, you are being tasked with ensuring the safety, serviceability, and durability of the infrastructure that forms the very backbone of economic and social development. So, whether you end up dealing with coastal engineering, earthquake engineering, or construction management, you are going to be applying the exact same core scientific principles to solve some really complex, real-world problems.
Moving on to Section 2, exploring major engineering fields and mapping out your specific engineering discipline.
Let's examine these different specialties, and honestly, I want you to think about it much like a medical student studying the interconnected systems of the human body. Just as a cardiologist focuses heavily on the heart while still relying on the nervous system, a structural engineer calculates internal forces, like bending moments and shear forces, while relying totally on soil data given to them by a geotechnical engineer. Now, if you decide to enter environmental engineering, your days are going to be spent managing public health, water treatment, and pollution control. Transportation engineers, on the other hand, focus on traffic flow and road geometry. And then construction managers are the ones who tie it all together by strictly controlling schedules, budgets, and manpower. However, before any of those fields can actually operate, we have to begin with surveying. Surveying is the absolute non-negotiable first step for all civil engineering projects. We use modern, highly accurate tools out in the field, like the total station, which digitally combines angle and distance measurement, alongside things like GPS and drone-based mapping. Listen, if your survey data is inaccurate, your land boundaries, your contour maps, and your entire structural layout will be drastically flawed. True safety and project economy begin right here with accurate surveying.
Now for Section 3, Mastering Basic Construction Materials. It's time to gather your essential tools.
With our map of the disciplines drawn out, let's gather our materials. These are the literal building blocks of your career. To build a resilient structure, you really must intimately understand that materials like molded clay bricks and natural igneous rocks contribute massive foundational structural strength to our buildings. Bricks, which are formed from clay and burned in high-temperature kilns, give us a perfectly uniform shape, low water absorption, and really excellent thermal insulation. Stones, harvested directly from igneous or sedimentary rocks like granite and sandstone, provide unparalleled compressive strength and weather resistance. That makes them the absolute ideal choice for retaining walls, bridge piers, and heavy load-bearing foundations.
Next up, let's talk about cement. Cement is your vital binding agent, and its actual performance relies strictly on a very precise chemical recipe. The chemical benefits of lime, which makes up about 60 to 67% of ordinary Portland cement, are completely responsible for the mix's strength and soundness. But you have to be careful. Excess lime actually makes the cement unsound. Then we have silica, sitting at 17 to 25%, which combines with that lime to form highly durable calcium silicates. Alumina is what helps with quick setting, and iron oxide gives cement its distinct hardness and that familiar gray color.
Now, to actually make concrete, cement needs some partners. You've got to understand the core difference here between fine and coarse aggregates. Fine aggregates, like river sand or manufactured sand, are small enough to pass through a 4.75 millimeter sieve. They act purely as a filler, closing up the tiny voids and improving the workability of the wet mix so you can pour it. Coarse aggregates, however, like crushed stone and gravel, get retained on that exact same sieve. They provide the bulk volume and are the major heavy lifting contributor to the final compressive strength of the concrete.
Think of mixing concrete a lot like baking a cake. It's a composite material. The water-cement ratio is your absolutely crucial recipe metric. When you mix cement, sand, gravel, and water perfectly, it cures into a rock-solid state. And we actually grade this strength. For instance, an M20 grade concrete means that after 28 days of proper curing, it's guaranteed to have a characteristic compressive strength of 20 megapascals. Lower grades like M10 are really just for leveling courses, while M20 and above are strictly required for actual load-bearing, reinforced concrete structures.
To finish up your material toolkit, you have to account for the forces that concrete alone just cannot handle. You see, concrete is amazing under compression, but it is remarkably weak under tension. Because of that, structural steel provides the vital tensile strength, ductility, and elasticity needed to resist dynamic wind and earthquake forces. Meanwhile, timber, derived from hardwood or softwood, offers a really great lightweight alternative with excellent workability and insulating properties, which makes it perfect for things like doors, windows, and temporary formwork.
All right, Section 4, Anatomy of Structural Elements. Let's understand the skeleton of your projects.
Now that we have expertly gathered our materials, let's piece together the anatomy of a structure. Visualize this as the very skeleton of your engineering designs, where every single bone has a specific, critical load-bearing purpose. Notice how the interconnected elements form a highly stable, rigid framework. We have the horizontal slabs acting as floors, horizontal beams supporting those slabs, and the vertical columns carrying all that accumulated weight downward to the foundation.
It is absolutely critical that you memorize this load transfer path. It's the fundamental rule of structural mechanics. Gravity is relentless, folks, and the load must safely travel step by step. It starts at the flat slab, transfers directly into the horizontal beam, pushes down into the vertical column, spreads out through the foundation, and finally rests safely into the Earth's soil. Slab, beam, column, foundation, soil. Commit that to memory.
Okay, let's dive into this specific cross-section of a load-bearing wall to observe some really specialized elements. Look right above the window. That horizontal reinforced concrete member is called a lintel, and it safely transfers wall loads away for the empty opening. Sticking out just above it is a cheja, which is an overhang protecting the window from rain. Moving down to the ground level, we see the plinth, the base above the ground. Crucially, a damp-proof course, or DPC, sits right at this plinth level. This establishes an essential, non-negotiable barrier to stop ground moisture from wicking up into the masonry wall and ruining your building.
As we reach the very bottom of our load path, we have to design the foundation itself. We generally classify these into two main systems. We select shallow foundations, like isolated or combined footings, when the topsoil near the surface actually has strong bearing capacity. But when we encounter weak topsoil, we have to switch to deep foundations, like pile or pier foundations. These drive deep down into the earth to completely bypass the weakness and anchor that massive building weight into stronger, deeper rock or soil layers.
Which brings us to our final section, common errors and final quiz. Let's review everything we've covered.
As we wrap up this lecture, it's my duty as your professor to ensure you're prepared for the actual realities of the field. Please make a mental note right now to avoid these common errors throughout your career. First, please avoid the ultimate rookie mistake of confusing raw cement with finished concrete. Cement is just the gray binding powder. Concrete is the hardened, finished composite of cement, water, sand, and stone. Furthermore, never guess on soil. Always perform proper geotechnical testing before ever selecting a shallow foundation. Never add too much water to your mix on site just to make it easier to pour, because it completely ruins the structural strength. And always ensure a damp-proof course is installed to prevent a lifetime of water damage.
I highly recommend taking a quick screenshot of this final reference slide. Consider this your master summary of building science and mechanics for your upcoming exams. Honestly, if you can confidently articulate the purpose of surveying, the chemical mechanics of cement, the distinction between compressive materials like stone and tensile materials like steel, and the overall load-bearing anatomy of a building, well, you are well on your way to mastering Unit 1. Let's test your understanding right now. Go ahead and close your notes for a second. Can you recall the exact path a load takes from the roof all the way to the earth? Let's see if you got it. It flows from the flat slab, transfers to the horizontal beam, pushes down the vertical column, spreads into the foundation, and finally settles deep into the soil. If you got that right, excellent work. I want to leave you with this final thought from our syllabus today. The materials, the formulas, and the mechanics that you master today are not just academic concepts to be memorized for a test and forgotten. They are the literal, physical foundation upon which our entire modern civilization is built. As future civil engineers, you literally hold the safety and prosperity of society in your hands.
Thank you for your incredible focus today. Now I leave you with one final question to ponder. What seemingly impossible structure will you dream up and build next?